Thank you, Mrs. Chairwoman, for that kind introduction, though I didn't really understand a word of what you said, but it sounded really great and impressive, so thank you for the introduction. Moreover, Louise, thank you for the invitation and all of your colleagues in the organizing committee to put on this amazing regional conference. You have a lot to be proud about. And this is my first visit to Costa Rica as well, and been having a lot of fun. It's just a beautiful country. I have to admit, after this, I'm not going to stick around and talk technical. I'm going to tour your beautiful country for 3 days after this, so just really appreciate the invitation. I was asked to talk about asphalt mixture performance tests, and I thought I would do that in the context of a topic that's becoming maybe popular again, and a powerful topic, and this is ground tire rubber modified mixes. So you heard Jeff Rowe talk a little bit about that, and the next speaker will talk exclusively about ground tire rubber applications on binder testing, and so this presentation fits neatly between their presentations. I recently moved from the University of Illinois to University of Missouri, where I started a new laboratory, and it has a comprehensive connection to industry, agencies, and academia. And the lab's called the Mizzou Asphalt Pavement and Innovation Laboratory, or MAPLE. And hopefully you can come visit us someday. We have a fairly large lab complex that we've built, nothing like the one that I just saw here at LANAM, which is truly stellar and world-class, but it's coming together nicely to serve the state of Missouri as well as the national and international research that we do. And so we have 2 labs on campus and 2 labs off campus as well. And it's all about asphalt, pavement, research, but also about innovation. So we do work outside of pavements in other areas of transportation and smart cities, intelligent infrastructure like battery-free wireless sensors that could be put into a pavement in a futuristic, future-looking smart city application. But we do work anywhere from binder scale, mixture scale, pavement structure scale, modeling, a lot of advanced modeling as well. And of course, we're interested in enhancing pavement sustainability. And so a lot of our work focuses on recycling technologies like I'll talk about today. And I think as Amit said in his presentation, you may not love the Hamburg test, but we found that to be a pretty useful tool. It's used for design along with volumetric mixture design in the United States, in quite a few states. And like the state of Illinois that I came from was an early adopter of the Hamburg test. So we feel like the problem of rutting is fairly under control in many locations, probably because our pavements have been becoming stiffer. The binders are getting a little bit stiffer than they used to be. And we have a lot of recycled materials making for some fairly stiff pavements. But the cracking now has become a point of major concern in the United States. And you'll see lots of research papers, lots of workshops and symposia that are kind of focused around developing a standard, fairly simple asphalt mixture performance test that can be used alongside volumetric mix design and alongside a high performance rutting test. And so we have all sorts of cracking. I've done, in my 20-year career, 20 plus years, I've done a lot of work on low temperature cracking and thermal cracking. I've developed tests and models and specifications, and so you'll see that is heavily woven into what I talk about today. But we have all sorts of cracking, anywhere from the transverse thermal cracking, reflective cracking, block cracking, and that can lead to other secondary forms of distresses like raveling and potholes. One of the early models that I worked on in Strategic Highway Research Program when I was a student at Pennsylvania State University was a model called thermal cracking, or TC model. And that was kind of characteristic of the tools we had at the time. We could do two-dimensional finite element modeling, phenomenological type models like Paris law to talk about crack evolution. But we always wanted to replace and update that technology with a true fracture mechanics-based test. And so as these technologies started to develop, we were really motivated to develop those tests to just have a better link between the lab test and field performance and improve those models, make them less empirical and more mechanistic. So one of the powerful concepts that we've used to develop both structural models for cracking and also to understand how these tests work and to improve them is a cohesive zone finite element technique that allows you to, in a fairly robust way, to propagate large cracks through a pavement like thermal cracks with minimal computational time. And so we've developed some models that look at the load displacement characteristics as a crack forms. What you find with asphalt is that it absorbs a lot of energy. It really is a crack resistant material, at least at first, until it starts to age or get moisture damaged. And you can see that because there's so much energy consumed after the peak local stress in the material is reached. And so any model where you're looking at coalesced propagating cracks really needs to take into account this energy that happens post-peak. And so some of the new tests that we've developed have really characterized the material in the post-peak. And then from there you can back up and develop a fracture-resistant pavement. But you have to be able to predict the cracking and then kind of back up and make your design stop short. We wanted to develop a test in a cylindrical shape. And we wanted it to be practitioner friendly, but accurate enough for research. And a geometry that had been used in other fields was a disc-shaped compact tension fracture. And so we modified what we found in the ASTM specification for other materials to work for asphalt. We had to change the hole size and location and increase the notch length a little bit. And this work was done as part of a National Science Foundation project more than 10 years ago. It was really done to try to address the reflective cracking problem. We have a lot of asphalt that's placed on top of old concrete or old asphalt, and there's always the chance that the joint or crack in the pavement below will propagate to the surface, and that was the original motivation. Later we moved this on to look at other forms of cracking like thermal cracking. And so it's once you get the specimen fabricated into the proper shape, it's a pretty simple test where you put steel bars through the holes that you've created, one fixed and one moving, and you pull the specimen apart, and that propagates a crack from the notch across the specimen. And then you're monitoring load, and then this clip gauge here measures the crack tip opening displacement, or CMO, crack mouth opening displacement, or CMOD. And so this test has been around for a while. It was adopted by ASTM in 2006. So it's been out for 11 years, and it's going through another revision this year. And this started to be put into specifications after the material specification was put forward. If you make specimens in batch, maybe make 8 or 10 specimens at a time, it takes about 10 minutes on average to do the cuts that you need to do and the drilling of the holes. So it's not terribly cumbersome. The machine is typical of asphalt binder or mixture test equipment. It's around a $50,000 machine. And the nice thing about the modern test machine that you can find from companies like TestQuip is that they're portable on wheels. They can plug into a regular wall outlet on a single 20 amp outlet. So they're pretty practical in that standpoint. We had a rather large a study that involved multiple states in the United States where we correlated the fracture energy that we get from the DCT test with transverse or thermal cracking. And we found a threshold value of around 400 joules per meter squared. And the mixtures that were above that value, we really didn't notice much thermal cracking in the field. We've done many, many more mixtures since this original study. But we definitely saw a high cracking on the mixtures that were down below 350, 300 joules per meter squared. And so we started to develop specifications where you could get higher reliability by having a higher fracture energy. And this temperature that you test at was similar to the philosophy of the bending beam rheometer. So you look at the low temperature grade of the binder, you add 10 degrees Celsius, and that's your test temperature. And it puts you in that quasi-brittle range where there's lots of thermal cycles in cold climates around that temperature. And we found that the results at that temperature were correlated to field cracking a little bit better than using just the low temperature grade of the binder, where the material becomes quite glassy and brittle at that temperature. And so the specification that we have been using, and it's been modified in different states around the United States, but in general, you're looking for about a 400 joule per meter squared fracture energy for low volume roads. And as you get to more important projects where cracking is to be less tolerated, then you can use a more conservative value of around 500 or 600 joules per meter squared. And so we've looked to apply both the Hamburg test and the DCT fracture test in intermediate and cold climates as like a balanced mix design approach. I remember 25 years ago when we had Marshall mix design, we had a volumetric mix design, and then we had a stability and a flow test. So we had some kind of torture tests or mixture mechanical test that went along with the volumetric design. I think that's where we're trying to get back to now, is to have, in addition to the volumetric design, also tests that really push the mix at high temperatures and low temperatures. What we found, though, is when you plot the results of a Hamburg and a DCT in a two-dimensional diagram, you get some fairly interesting trends that come out. And so the concept that I want to use today is a performance space diagram. And what you're looking for are mixtures that are in the upper right-hand corner where they have a low rutting result and a high fracture result. And because we only have one rutting level, 12.5 millimeters, most specifications, but we have multiple traffic categories for the thermal cracking test, we have 3 performance zones that we're looking to be in, one for low traffic, one for medium, and one for high traffic. For the ground tire rubber study I'm about to show you, we were designing on a heavy interstate pavement in Chicago, and so we were designing all of our mixtures in this box out here. So we'll focus on that today. Some interesting trends as we started to look at mixtures in Illinois. We saw that if you had a poor mix with a weak aggregate and a soft binder, it would fail in this hot zone here for rutting. But if you were to take a binder with a similar spread between the high and low temperature grade, it may not fix the mixture. You may just move into failure and cracking. So really, you have to, when you have a weak aggregate system, you're either going to have to improve that or use an improved binder, but just changing the viscosity characteristics of the binder doesn't necessarily save a mixture. But when you look at polymer modified mixtures that have a bigger spread between the high and low temperature grade, higher levels of SBS modification, for instance, then you do see that instead of trading off the properties along this axis shown by the red value, then you start pushing into that performance zone that you want to be in. And so as you look at binders with more than 100 degrees Celsius spread between the high and low temperature grade, you can start to develop high traffic, high performance mixtures. You can also do it with other methods. This is one that illustrates when we use recycled roofing shingles. They have a slightly positive effect in pushing us more towards the corner here, but rather than just swapping the virgin binder grades. If you use a considerably stronger aggregate, we compared a weak limestone versus a strong gravel. It improved the rutting resistance and improved the cracking resistance of that mix, and so that shows the investment in a better aggregate system. When we develop very high performance mixtures like stone mastic asphalt, they perform drastically different than dense graded mixtures with lower amounts of polymer modified binder. So when we invest in a stronger rock with a better gradation, polymer modified binder, thick films of asphalt, we truly do get to a very high performing mix. And we know that these mixtures work very well in the field. We can also design very high recycled content mixtures. I call this asphalt binder replacement. So you're replacing what would have been new virgin binder with recycled binder, either from recycled asphalt concrete or maybe roofing shingles. And so we can replace anywhere from 30 up to 67% binder and still be in some of these passing zones. They may be more suitable for low volume roads where you can tolerate a little bit of cracking for an economical, sustainable design. So moving on to ground tire rubber. And we'll hear a little bit more about the sustainable aspects and the motivation from the next presentation, so I'll go through this quickly. But obviously throwing tires in a landfill is not what we want to do for sustainable practice, and it can even be a dangerous endeavor. You know, these sometimes will catch on fire and you really cannot put them out. What we found recently, ground tire rubber is becoming finer and finer. The manufacturers are finding ways to make the size of the particle very small, maybe fitting through a number 30 sieve or a number 50 sieve. The particle size is getting quite small, and the processes are becoming more sophisticated. And so the quality control of these products has improved. Early on, 20, 30 years ago, there were some reported failures, and sometimes the rubber will settle or it will be variable throughout the project or just not done correctly. Maybe it creates a high viscosity that makes it hard to work with. A lot of those problems have been addressed by modern manufacturers, and so there's even some new dry process where we put the rubber in at the last stage in mixing, and I'll introduce one of those new processes here in a moment, and they're performing much better. And don't think of this as just a place to use a recycled material. Everybody wants to put stuff in asphalt. I'm an editor of an international journal. I can't tell you how many papers I get from around the world where people want to put anything in asphalt, from glass to fibers coming from various waste streams. And some of it works out very well. Sometimes there's just some things we shouldn't put in asphalt. But clearly, it's more than just filling space with the material. We can see enhanced performance properties with ground tire rubber. It really does improve some of the characteristics of the mixes you'll see, and that should be a motivation beyond just recycling. So we put these to the test in a very high traffic environment near Chicago, Illinois, and this was on the tollway system and on a route Interstate 88, just west of the city. And we actually looked at 9 different mixtures. And the idea was to look at 3 different rubber technologies, two that were kind of a terminal blend process, and 1 that was a new dry process. And we wanted to look at 2 different recycling levels, 33% recycling binder replacement and 47%. And we wanted to look at some different binders. And so the first 2 columns that you see here have 33% recycling or asphalt binder replacement. The last column here has 47%, and that's done through the use of recycled asphalt concrete, RAP, and recycled asphalt shingles, or RAS, which are very, very stiff. And so that's their 3x3 matrix. The 2 products on the top and the bottom were terminally blended, and the middle product was the dry rubber process. A little bit more about those. So again, the first and the last were terminally blended ground tire rubber, whereas the middle was the dry process. And the last product is a new one that involves both SBS modifier and ground tire rubber. The first product is the one that's most commonly used in Chicago, and they've placed 10 million tons of this product in the last 5 years. And so it has some heavy usage now in the Midwest United States. Since you may be less familiar with the new dry process, a few slides, the way this works, and I think Jeff alluded to this before, he even talked about a blue fiber feeder, and literally on this project there was a blue fiber feeder. So they use this for putting fiber in stone mastic asphalt. We didn't need fiber in these SMAs because of the way the rubber swells and gels up the mastic. There's no drain down, there's no need for fiber. You have these large totes that are dropped into this fiber unit. You can see there's paddles down here, so it's like a pug mill mixer. It just breaks up the ground tire rubber. And then it's hard to see in this picture, but there's a tube that goes into the place in the drum towards the bottom where the recycled asphalt goes in. In that same location at the bottom third of the drum is where you blow in, pneumatically meter in the rubber. And so you can watch the rubber flowing through the tube. It's a clear pipe. And this mix, somebody was talking before about having 5 or 6 modifiers in a mix. I think it was Louise. And actually on the mixture side, we had ground tire rubber, recycled asphalt, pavement, recycled asphalt shingles, and warm mix asphalt, not to mention the other modifiers that were in the binders. So there was quite a few things going into these mixtures. It's a real challenge to try to characterize these mixtures purely with the liquid binder test, because the way all these things go together in the field, they don't completely mix. I will tell you that the roofing shingles are so stiff, their melting point is higher than the temperature of production. So those roofing shingles are partially melting. I think the same thing is true of the wrap. Not all of that wrap binder is melting and mixing. So we have a very composite material, especially when you add the rubber. And these mixture tests give us a very good feel of how it all went together. And so we ran the low temperature cracking DCT test, the Hamburg tests. The Hamburg wheel tracking test, we followed a lot of the guidance out of Texas. We used a fixed temperature of 50 degrees Celsius, and for higher traffic levels, we use higher number of wheel passes. In this case, we used the highest typical number used, which is 20,000 wheel passes, and this was also done submerged. In case there is a propensity for moisture damage, we wanted to be able to capture that. Looking at the fracture results first, this is the DCT fracture results. These are on the plant compacted materials, and the trend we expected to see is when we went from the -28 binder to the -34 binder, we expected to see a pretty big boost in fracture resistance or fracture energy. But then as we added higher recycling, we expected it to come back down, and that's what you saw. And for each of the three conditions for the mixtures, you saw the similar trend. When we tested the field cores, it was interesting that we actually had slightly higher fracture energies when they finally produced these mixtures. That's good. Sometimes in production, you'll see the performance properties go down as the contractor maybe rushes to complete the project. It's not as good. But in this case, we had better properties in the field. And again, we saw this trend of higher fracture energy for the -34 binder, and then with the higher recycling, the properties came back about where we started. But in many cases, the final properties in the last group of bars was better than the initial property, which said that higher recycling plus a softer base binder gives you a good comparison to the control section. But we did see that the Seneca product was the softest, most fracture resistant of the three products. But when we compared to our specification, all 9 mixtures had a suitable fracture resistance. We also ran another cracking test just to compare to see if we would spot the same trends. Don't want to spend a lot of time talking about it, but this was a semicircular bend test. And we saw a similar trend of highest resistance to cracking in that middle group with the -34 binder. But I would say that all 9 of these mixtures failed the cracking specification for the semicircular bend, which doesn't really match with the field performance, at least that we've seen with the first group. So probably need to revisit the specification for this test. The Hamburg results were all good. We had one higher Hamburg result. It was well below the 12.5 millimeter allowable rut depth, and that was the softest mixture with the Seneca terminal blended GTR product and the -34 base binder. But where it gets really interesting is when you plot these Hamburg and DCT pairs together on a performance space diagram. And what we've seen in the past is that for a similar aggregate structure, if all you do is change the characteristic of the binder or the mastic, the points fall roughly on a line. And that's what we saw here. The Seneca product had the highest fracture energy. It's furthest out to the right and fell along a line. The dry process, the ECR product, and this is the least expensive product, and the contractors feel like it's the easiest one to use. So the contractors like this new dry process. It fell in the middle, and then the other new terminal blend process, RMA product, fell on the stiffer side with the lowest rutting and the lowest fracture resistance. But they did follow this trend. What's interesting in this data set is that the slope of this line is fairly flat compared to the other trends that I've seen. We've had more diagonal lines on the performance space diagram. I think that has something to do with the role of the swelled ground tire rubber. And what it suggests to me is that there's an opportunity on these mixtures to use a very soft base binder and still resist rutting fairly well. It may be that we've been designing these mixtures a little too stiff. They seem to be very tolerant to a soft virgin binder, and that can probably push us, pretty far out into the performance space here. Whereas other mixtures, when you use a softer binder, it may push you down more in this direction towards failing the running test. So I thought that was pretty interesting. So we have a little bit of ongoing work, and one is creep compliance testing with the DCT test, and also that thermal cracking modeling that I spoke about before. So we wondered if we could do a fixed load test on this fracture geometry prior to fracture testing. And these are the type of creep compliance master curves that we get. And so I was also wondering if the same trends in fracture energy, when we rip the specimen apart, would be seen in the rheological mixture test. And sure enough, we saw the exact same trend, where the -58 binder was in the bottom set. As we add the -34, or substitute to -34, the creep, the ability to relax stress is improved. It's just like getting a better bending beam M value or a lower stiffness. But then when you add the higher recycling level into 47% recycling, you go back towards the control mixture. So the thing that we saw for fracture energy, we also saw for creep compliance. Same thing for the Elastico mix. We saw the same trend of softer, more compliant mix with the -34 binder and back to towards the control. And the stiffest mix was the EvoFlex, and it showed a less spread but a similar trend. So I'm probably getting a little long on time, and just probably focus on the bottom bullet. I think this is really good for the marketplace to have not just one ground tire rubber product that can be used in a region, but now we have 3 different products that perform a little bit differently, but they all pass the specification, and we're seeing the price drop. So after this study, which was done about 1.5 years ago, the price of the incumbent, the Seneca GTR product, dropped by about 50%. So another lesson of the story is it's good to have multiple products that can get you to the finish line, to give you choices and to give you, I think, a better bid price in the environment. But the key to moving this forward, I think, was the mixture performance test, because up until this point, these mixtures were a little bit taboo. There was this people were remembering the failures of 20 or 30 years ago, and so it took, I think, these performance tests and these field trials to get things going again in this part of the United States for this technology. Thank you very much for your attention.
Muchas gracias por la presentación. ¿Algunas preguntas para el Dr. Buttler?
I think we're waiting for the microphone.
Thank you very much, sir. I was wondering if you could maybe elaborate a little bit more on the new dry process versus the old method?
Yeah, so the new dry process, what it requires is, as the ground tire rubber is blown into the asphalt drum plant, it mixes with the binder and it starts to react. In fact, it doesn't react very much, but what it does is starts to swell. And by the time it goes through storage in the storage silo, and goes to the field and is paved, it's really fully swelled. Whereas the other products are reacted at a terminal. And so they're blended and sheared, and they need to be continually stirred as they're transported and pumped. And the challenge with some of the wet processes or the terminal blend processes is that you have to be very careful that things are continually agitated, otherwise the percentage of rubber can vary on the project. The dry process, in a sense, I would be careful saying this, but as a contractor, you see the rubber go in, you're weighing the amount of rubber, so there's a scale on the blower, so you have a very good record of how much rubber is going in at what rate, and you can see the rubber going in. Jeff and I were talking, there's a chance that the rubber could blow around if there's a vacuum system, as there always is in a drum plant. You have to make sure that these light particles aren't sucked out before they get incorporated. But what we are finding is that when you do extraction and recovery on these mixtures to obtain the binder, if you sieve or otherwise characterize, you'll find the rubber particles in all three of these, not just the dry process. So the rubber is creating a composite rather than being somehow ingested and creating a fully integrated microstructure. They're discrete particles, but that's probably good for crack arrest because they're so swelled and so prominent that a crack or a microcrack is going to hit one of these particles. It's really hard for cracks to get around them.
Very nice presentations. One question: which of this process you think is the one that affects the less the environment? Because I've heard that we need a lot of heat to produce the mixture. So we are not affecting throwing the wheels, but we affect the environment.
Yeah, we haven't finished our life cycle assessment of these. Others have started that work. I am very, very confident that our next speaker, who's just about to be introduced, he's also an expert on life cycle assessment. I think I'll defer the question to him. But you can imagine that this is a good reuse of these materials. But in terms of the relative ranking, I think we just need to do that research because the energy and production will be a little bit different on these. Probably the performance prediction, life prediction will be a little different on these.
And another question, do you think that the normal approach to measure the fatigue in the asphalt mixture applies also for these kind of mixtures with rubber? Or
so the question is,
do we need different approaches and different models to account the fatigue in this kind of?
I don't think so. I believe if you have a good test, even if it's not a purely fundamental test and model, I think even most of the torture tests are appropriate to apply to these. Yeah, I think you have to be a little careful. I know when you run these in 4-point flexural fatigue in controlled strain, you can get some sometimes outlandishly high, like overly positive results. In the fracture test, when we cool it down to low temperatures and fracture it, you do get a nice bump in fracture energy, but it's not like orders of magnitude. Sometimes the fatigue test results, you can see some almost unbelievably high fatigue resistance, but I don't think it would be that much better in the field.
Thank you.